Hello, let's talk about the refrigeration action বা let's talk about the refrigerator. আমাদের বাড়িতে যে ফ্রিজ রয়েছে সেটা কি ওয়ার্কিং প্রিন্সিপালে কাজ করে এবার সেটা আমরা ডিসকাস করব। নাও রেফ্রিজারেটরটা হচ্ছে এমন একটা হিট ইঞ্জিন which is operating in the reverse direction as the original heat engines. Now heat engine generally absorbs heat from the hot reservoir, performs some work W and liberates Q2 amount of it to the cold reservoir. Principle of refrigeration is exactly opposite. It absorbs Q2 amount of it from the cold reservoir. W amount of work is given as input to the engine and it will liberate Q1 amount of it to the hot reservoir. Refrigeration এর পারপাসটা হচ্ছে we must get a maximum amount of it Q2 from the cold reservoir with the expenditure of minimum work done by W. মানে সর্বনিম্ন কাজ করে আমরা যে সর্বোচ্চ Q2 টাকে অ্যাবজর্ব করাটা from the cold reservoir এটাই হচ্ছে রেফ্রিজারেশনের পারপাস। আইডিয়াল রেফ্রিজারেটর যদি হয় তাহলে W will be minimum and Q2 will be maximum. মানে maximum Q2 absorb করতে গেলে minimum work done বা minimum W হতে হবে। Now here the output is the heat extracted from not the hot reservoir but from the cold reservoir. Heat engine এর জন্য কি ছিল আমরা hot reservoir থেকে Q1 amount এর heat absorb করছিলাম কিন্তু এখানে cold reservoir থেকে Q2 amount of heat টা absorb করব। Now input for this case is the work done into the engine. So here we defined as coefficient of performance. Coefficient of performance is the amount of heat extracted from the cold reservoir divided by the amount of work done into the engine. And here যেহেতু Q2 amount of heat is entering into the engine, so Q2 is equal to positive and Q1 amount of heat is getting liberated from the engine, so Q1 is negative. We are taking the magnitude of Q1, that's why. So W is equal to Q1 magnitude minus Q2. So in place of coefficient of performance we could write this as coefficient of performance হচ্ছে Q2 by W. W টা আমি দেখলাম Q1 এর magnitude minus W. So coefficient of performance equal to Q2 by Q1 magnitude minus Q2. This is the heat extracted from the cold reservoir divided by the work expenditure বা refrigerant বা ওয়ার্কিং সাবস্টেন্স হিসাবে যে ফ্লুইডটা এখানে ইউজ করা হয় তার উপরে যে ওয়ার্ক ডানটা করা হচ্ছে। এখন রেফ্রিজারেন্ট বা ওয়ার্কিং সাবস্টেন্স হিসাবে এখানে সাধারণত ফ্লুইড আর ভেপারের মিক্সচার থাকে। সামটাইমস এখানে সালফার ডাইঅক্সাইড, মিথাইল ক্লোরাইড বা অ্যামোনিয়া এইগুলো ওয়ার্কিং সাবস্টেন্স হিসাবে কাজ করে। নাও হোয়াট ইজ দ্য ডিফারেন্স উইথ দ্য হিট ইঞ্জিন? হিট ইঞ্জিনের ক্ষেত্রে আউটপুট যেটা সেটা হচ্ছে দ্য নেট amount of the mechanical work. So the net output is the amount of the mechanical work done by the engine. But here mechanical work টা কিন্তু the refrigerator needs as input. মানে এখানে mechanical work টা ইঞ্জিনের ইনপুট হিসাবে সার্ভ করছে। Let's discuss about some practical refrigerator. This is the schematic energy flow diagram of practical refrigerator. এখানে সার্কিটটা হচ্ছে ফ্লুইড সার্কিট কারণ এখানে পুরো সার্কিটের মধ্যে কারেন্ট নয় ফ্লুইডটা অপারেট করছে। ফ্লুইড ইজ ফ্লোয়িং থ্রু দিস সার্কিট, তাই আমি সার্কিট কথাটাকে এখানে ইনভার্টেড কমার মধ্যে রেখে দিয়েছি। So here the working substance is the refrigerant. রেফ্রিজারেন্টটাকে আমরা ওয়ার্কিং সাবস্টেন্স হিসাবে বলতে পারি। Now on top একটা condenser coil থাকে। A condenser coil is serving as a hot reservoir which is kept at temperature T1. এটা হচ্ছে একটা কোল্ড রিজার্ভার এখানে একটা evaporator coil থাকে which is kept at low pressure and low temperature, আর hot reservoir temperature এবং pressure দুটোই higher হয় than this cold reservoir. দুটোই একটা করে coil. Condenser is itself a coil, evaporator is itself a coil. Condenser is kept at a higher pressure and higher temperature. Evaporator is itself a coil too, and it is kept at a lower pressure and lower temperature. Now let's come to the refrigeration action. Refrigeration action ta ebar amra ekটু bhalo kore bujhbo. First I will tell this in English, then I will repeat this in Bengali. This is the compressor. What the compressor does is it compresses the fluid working as working substance by refrigerant. So this compressor first takes in the fluid into itself. Here the fluid gets compressed adiabatically, that means no heat exchange, and then from the compressor it is delivered to the condenser. Now the temperature of the fluid is higher because of the compression than that of the air surrounding the condenser. So the refrigerant or the working substance leaves off a certain amount of heat, say Q1, and as it leaves off heat, so it gets condenses partially to liquid. The fluid then expands adiabatically to this evaporator, and the rate of flow of liquid or fluid from this liquid storage to this evaporator is being controlled by this throttling valve. Now as the fluid expands, as a result of expansion, it cools considerably, and it is considerably gets cold, so that the fluid in the evaporator coil is colder than its surrounding. So it absorbs heat from the cold reservoir, and the amount of heat absorbed from the cold reservoir is Q2. So here cold reservoir is actually the matter or the material which we want to be cooled. Suppose we have kept a basket of vegetables, so then for the evaporation the working substance will take off heat from those vegetables, and those vegetables will be cooled off. So the liquid fluid which is acting as a working substance, it takes in heat, that is absorbs heat Q2 from the surrounding, cooling them and partially get vaporized. Again the fluid enters into the compressor to begin another cycle. Now the compressor is actually driven by an electric motor which requires some energy input, and it does some work W on the working substance during each and every cycle. Now let's think of air conditioners. Air conditioners operate on the same principle of refrigeration, but in this case the refrigerator box is the entire building or the room. The evaporator coil is kept inside and the condenser coil is kept outside. Now for large installations, the condenser coils are often cooled off by water. For air conditioner, the quantities of great practical importance are the rate of heat removal and the power output. So here we define the power input. So here we define the power input P equal to work input divided by time, and heat absorbed from the cold reservoir is defined as H equal to Q2 amount of heat absorbed from the cold reservoir over time. So performance coefficient of performance will turn out to be H by P. The typical value of H for an air conditioner will be like this. It's about 1500 to 3000 watt, and for that we need electrical power output of 600 to 1200 watts. And for these values of power input and H, we will have K equal to 3. This is the typical value of the coefficient of performance for air conditioners. Now let's think about heat pumps. Now heat pumps basically operates on the principle of refrigeration in the same way as air conditioner works, but here we can think of a refrigerator which is turned inside out. These heat pumps are used to heat buildings by cooling the outside air. It functions like a refrigerator turned inside out. Here the evaporator are kept outside. They take heat from the cold air, and the condenser coils are kept inside, and they give off heat to the warmer air. With the proper designing of the circuit, we could get a considerable value of the heat absorbed Q2 per cycle, which can be greater in a huge amount than the work W required to get it there. Now what we think about workless refrigerator? What is a workless refrigerator? And workless refrigerator is something where without any work input we will be able to deliver heat from a colder to a hotter body. So coefficient of performance becomes K equal to Q2 divided by 0. Work input is 0 here, so it's K equal to Q2. I'm sorry, this is not Q1, this would be Q2. So it's Q2 divided by 0, which turns out that coefficient of performance to be infinity. And this is like a myth, like a free lunch. Can we cool off our room by leaving off the doors of our refrigerator? Please put your answer in the comment section. Now let's talk about second law of thermodynamics. There are so many experimental evidences which strongly suggest that it is impossible to build a heat engine that converts heat completely to work. That is, we can't have an engine with 100% thermal efficiency. This impossibility is actually the basis of the statement of second law of thermodynamics. So we could state second law of thermodynamics as follows. This is the statement. This is impossible for any system to undergo a process in which it absorbs heat from a reservoir at a particular temperature and converts that heat completely into mechanical work. Now, mechanical work is the useful form of energy. With the system ending in the same state in which it began. This statement we can also call it as Kelvin-Planck's statement of second law of thermodynamics. Now the basis of second law of thermodynamics is the difference between the nature of internal energy and that of macroscopic mechanical energy. In a moving body, inside a moving body, molecules are moving randomly, they are interacting with them, and as a result of their interaction, potential energy arises. But there is also a macroscopic motion of the body. I mean, along with this random motion, there is a superimposition of a coordinated motion, macroscopic coordinated motion, which leads to macroscopic mechanical energy. So, the kinetic energy associated with this coordinated macroscopic motion is what we call the kinetic energy of the moving body, and the kinetic and potential energies associated with the random motion constitute the internal energy. And the basis of second law of thermodynamics is the difference between the nature of the internal energy and the macroscopic mechanical energy. Now, when a body is sliding on a surface, let's think of a wooden block sliding on a surface which is having a reasonable value of friction. So when it comes to rest, as a result of friction, the organized motion of the body is converted to random motion of the molecules in the body and of course in the surface. Now, we are not able to control the motion of the individual molecules. We cannot convert this random motion completely back to organized motion. We can convert only a part of it, and this is exactly the working of a heat engine. Now, if the second law of thermodynamics were not true, we could power, for example, an automobile, our car, or we could run an entire power station by just cooling the surrounding air. Now, neither of these impossibilities violate the first law of thermodynamics, but second law of thermodynamics tells us that there is a limitation of the availability of energy and the ways in which we can use it and convert it. So there is a difference between the first law and second law. We cannot derive second law from the first law. It stands on its own as a separate law of nature. The first law denies the possibility of creating or destroying energy, but the second law limits the availability of energy and the ways in which it could be used and converted.